Good. So good afternoon, everybody. We've got this session starting with Kevin Limanta, and he's going to be speaking on super Catalan numbers and Fourier summations over finite fields. Thank you, Kevin.
Okay, thank you, Carrie, for the introduction. So thank you, everyone, for coming to this talk. So I will be talking about the super Catalan numbers and its connection to Fourier summations over finite fields. Okay, so I promise I won't assume any knowledge apart from just basic undergrad knowledge. I promise to keep it simple, and this should be quite simple, and actually the result is quite surprising to me, at least, that there is this curious connection between these super Catalan numbers, which I will introduce in a second, and its problem to the integration over finite fields in some sense. Okay, so let me begin by talking about the motivation. So we want to actually make sense, at least how to set up some integration theory of polynomials over circles. So basically Fourier analysis sort of setup, but when the underlying field is finite. Okay, and of course this means that, well, yeah, as mentioned, this will be some sort of foundation of Fourier analysis over a finite field, but the function will take value in the field itself or its field extension. Okay, so no real value function or complex value function, as we know in the usual story. And we're considering not just the Euclidean geometry, so the unit circle will not be the usual x squared plus y squared equals 1, but we are also considering the relativistic geometry as well, and we will see that these geometries are connected, pretty much connected. Okay, so let me begin by introducing the super Catalan numbers. So, oh, this should be not the year is not correct. So this should be 1874. Of course, it's not gonna be. Doesn't make sense. Okay, so introduced by Catalan himself, the super Catalan numbers. So these numbers generalize the well-known Catalan numbers. So when m is equal to 1, you will see that these numbers will be twice the usual Catalan numbers. Okay, and these, because these are always integers, they have some combinatorial interpretations so far that we know of, in terms of blossom trees, cubic trees, dyke paths, Motzkin paths, lattice paths, and of course these combinatorial objects satisfying up to some conditions, up to some restrictions. Okay, so the last one in the interpretation in terms of lattice paths, which was introduced by Georgiadis, Munemas, and Tanaka back then in 2012, that will be particularly important to our story. Okay, so before we actually mention about its connection to the lattice paths introduced by Georgiadis, Munemas, and Tanaka, these are some values of the super Catalan numbers. Okay, you can see that not very trivial here is that the first column, they are the central binomial coefficients, and then these second row, or maybe first row if you want to start your index from 0, they are the Catalan numbers multiplied by 2. Okay, and so these are basically the things I just mentioned, and maybe a not so trivial observation we can see here is we have a Pascal-like property. Okay, that if you start with any entry, okay, multiply that by 4, that will be the sum of the entry to its right and the entry to its just below that. Okay, so for 48 here, which is 4 times 12, is 20 plus 28, and this is true for any entry. Okay, so Georgiadis, Munemasa, and Tanaka observed that we can actually relate these super Catalan numbers to Kraftchev polynomials, which I'm sure you guys know. So these are pretty known polynomials connected to coding theory, harmonic analysis, probability theory. And I won't actually talk much about this Kraftchev polynomial, but one implication that we can see here is that if we think about the generating function of the Kraftchev polynomial, so so the right hand side here is, you can think of it as generating function of the Kraftchev polynomial. So the central term of this polynomial, okay, which is the coefficient of the alpha to the m plus n here up to some sign, is actually our super Catalan numbers. Okay, so this will be our identity that we will use quite often in this topic. Okay, and one variant of the super Catalan numbers, which I define to be circular super Catalan numbers, because its connection to a circle. It's basically just this super Catalan numbers, but you divide by 4 to the m plus n. So you scale down. No, so it's no longer an integer, but rational number. And when I actually talk about its reduction modulo p for any odd p, prime p, it is well defined because this SMN is always an integer and the denominator is never a multiple of p. Okay, so it's well defined, and well, because I divide by 4 to the m plus n, then this this equality makes sense. Okay, I divide by 4 to the m plus n practically both sides. Okay, so this is the table, and now what our Pascal property becomes is indeed the actual Pascal property, that if I start with any entry, then it will be the sum of the entry to its right and the entry just below that. Okay, so this is exactly the Pascal-like property that we see in Pascal triangle. Okay, okay. Now let's define the like if we want to talk about unit circles and the integral in this sense, let's define the circle first. So we start with any finite field of q elements, where q is some power of some prime p, odd prime p. So we define, well, we impose a geometry. Okay, so by defining this bilinear form, respect to this matrix, like symmetric matrix M, and we are interested in 3 special cases of M, K, so I, J, and K. So I will give you just the usual Euclidean geometry. J and K will give you like non-Euclidean geometry. Okay, so we have 3 geometries, and I will call the 3 circles that can be constructed by this bilinear form. The green, red, and blue. So the subscript G, R, and B stand for green, red, and blue. So the blue one corresponds to when M is equal to I. The red one corresponds to when M is equal to J, and the green one corresponds to when M is equal to K. And this choice of presenting it in this order is deliberate, because I want to present this in ascending order of complexity. Okay, so the green one is the simplest, and then you have red, and then the most complicated one in this setup is the blue geometry. Okay, so okay, so before we actually talk more about the integral, so in the blue geometry in particular, there is like a problem whether -1 is a square number or not. So we want to capture that distinction by what we call, like, well, Lysander symbol when we are talking about like prime fields, but then when in general we want to capture that through the Jacobi symbol. Okay, so it's quite well known, and we can use this Jacobi symbol to capture the size of our unit circles. So the green and the red circles, like it's pretty straightforward to count the number of points on the circle to be q minus 1 if the size of the field is q. But then in the blue situation, the size of the circle depends on whether minus 1 is a square or not. Okay. Right. So this will be our notion of integral. Okay. So we want to come up with some sort of analog of our integral defined for polynomials over our field f to the field itself, and we call that functional circular integral functional, precisely when this functional satisfies three conditions. First one is called normalization. It's just plain old normalization that we want 1 to be mapped to 1. Okay, but then locality here is basically saying that if your polynomial is 0 on the circle, then its integral ought to be 0. Okay, and the invariance is basically saying that your integral should be invariant under rotation and reflection. So these three are what you would expect in integrals in the classical sense. Okay, so we don't actually impose something new. Okay, we come up with something like purely algebraic without coming up with like a notion of limit or infinite processes and stuff. Okay, right. So of course, when we talk about like integrating polynomial over a circle when the field is finite, the three most natural candidates, well, in its geometry, will just be taking the sum of the function value and then over all points on the circle. Okay, so this will be our well, one notion of integral, and it might be well, you might ask, well, why is there a negative sign in front? But they are just there just to because we want them to satisfy the three conditions that we imposed earlier. So we can check that these three functionals are indeed circular integral functional. Okay, that's easy. But a slightly not so trivial one is to show that these are the unique circular integral functional. Okay, so we can show that these three are basically in its geometry the integral that we have. Okay, the integral that we have. And okay, so that's good. Okay, and I won't be talking about this uniqueness, existence uniqueness aspect of these functionals. I want to actually talk about the formula. Okay, so one might ask, okay, if we have these three functionals, okay, that's good, but can we actually have some sort of formula? Okay, nice formula to these three functionals. Okay, and that's where the super Catalan numbers come in. Okay, so let's have a look at an explicit formula for this psi sub g. So basically just this functional here. And in this case, it's very easy. Okay, so its value is either 1 or 0, and there is this divisibility condition. Okay, and this 1 sub q is just our notation for like the 1 in our field. Okay, the multiplicative identity in our field. And the proof is very simple. Okay, so it's actually not very complicated. So this problem of integrating over the green circle amounts to just taking the sum powers of x in our multiplicative subgroup of our field. Okay. Okay, so I'm not gonna talk much about this. Okay, but the formula that will incorporate the super Catalan numbers happen in the red and the blue situation. Okay, so in the red situation, okay, so if I define f sub kl to be this polynomial, then what we have here is if I want to integrate this monomial alpha to the k, beta to the L, so which I can do because our functional is linear, in the red geometry, then what I need to do is I take this polynomial and just extract some suitable coefficients, okay, and then take the sum, reduce that modulo p, okay, either that or 0. So it's either this one or this one. And of course, in the formula, when the powers are all even, we have some sort of geometric constant that depends on the size of a circle. Okay, so we have W and R here to be our geometric constants. Okay, now I will illustrate this in some example. Okay, and you will see that in the blue situation, it's pretty much the same, except that we have this -1 to the n in appearing in front. So it's pretty much the same. Okay, we have our polynomial, we are extracting some coefficients, take the sum and reduce that modulo p. Okay, and note that this will be always in our field. Okay, and in fact, it's always sitting inside the prime field. Okay. Okay, so I want to actually talk about its connection to the super-Catalan numbers. So when the degree of the monomial is small, okay, in this case less than q minus 1, then our geometric constant, one of our geometric constants, r will become 0 in this case, and so we just have the central term basically of this polynomial, and that will be our, well, in this case, circular super-Catalan numbers. Okay, omega mn. Okay, so we have this nice theorem that if the degree of the monomial is less than q minus 1, then we have basically our integral can be captured by the super-Catalan numbers, circular super-Catalan numbers. Okay, so as an example, let the size of the field be 13, for example. So -1 is a square in this field. And so if I want to find out what the blue circle is, the usual Euclidean circle is, then I can have this set of points. There are 12 of them, 12 points. And in particular, if I want to integrate alpha to the 4th beta square, then all I need to do is just compute or find omega to 1, in this case 1 on 16, up to some sign, reduce that modulo 13, and I get 4. Okay, for example, if I have like a slightly bigger field of size 25, I can identify our field as just a plus b omega, okay, omega squares 2. You have this set of points on the red circle. And if I have like this monomial, so big enough powers, all I need to do is with this polynomial, I find these 5 coefficients, okay, take the sum and reduce that modulo 5, that will get 2, okay. And the central term here corresponds to our circular super-Catalan numbers. Okay, so I want to actually, in the last couple of minutes, want to talk about the possible generalization of the super-Catalan numbers, because I mentioned earlier that the super-Catalan numbers are the coefficient of the central term of this polynomial. Okay, but then what about, okay, one might ask, what about the terms close to the central term? Say 1 step away from the central term, 2 steps away from the central terms. So I define this S sub k, okay, so it's the coefficient of m plus n plus k, okay, of this polynomial. And of course, it's symmetrical, so it doesn't matter if I have plus or a minus sign here, it's the same. But what else do we know about these numbers? So I want to actually capture that like list of integers in this table. So in this case, when k is equal to 1, we have this table, and you see that immediately, okay, there's 0 in the diagonals. What else can we say? And well, we can come up with this formula. Okay, it's similar to the super-Catalan numbers, except that you have this m minus n, and then you have this m plus n plus 1. Okay, what about S sub 2? Well, S sub 2 will be given by this table with at least the first few values. You can see that, okay, maybe I should have said this earlier, but the Pascal-like property still holds, okay? But because we're talking in the sense of like super Catalan numbers story, so anytime you come up with some entry like maybe this one here, you multiply that by 4, it will be the sum of, but in this case, it's not exactly the same because up to some sign, I have to, so if you multiply this by 4, and then you add the term next to it, you will get the term just below that. So the Pascal-like property is still there, but it's slightly different in this case. Okay, and one can come up with this formula for S sub 2. Okay, so just like 1 more minute. I can come up with this formula for S sub k for at least when k is up to 4. I don't have enough space to put all the other values, but you can see some nice property about this p sub k. It's controlled by this p sub k, and you can see some symmetry appearing in this polynomials. And I will close this by talk by this conjecture. I'm trying to get my head around that the generalized super Catalan numbers are of the form like this. Okay, when p sub k is a polynomial of degree at most k in M and N. Okay, and this is up to, I believe I still cannot find like some literature that at least mention these polynomials. So I'm still trying to figure out what these are. Okay, so I think I can stop now. So thank you very much for listening.